I would like to invite the next presenter, Mr. Wee. His topic is on low cycle and high cycle fatigue of mismatched, low carrying welded joints. Please.
Hello everyone. My name is Song Wei. I come from the Harbin Institute of Technology, and now I'm an exchange student in NTNU. Today I will present my work about the low cycle and the high cycle fatigue assessment about the misattachment load carrying cruciform welded joint. And this work will be presented as the following 5 parts. The first part is about the motivation about my work. For the shipbuilding and the marine structures will be built as the high cycle, high strength steel, and even using the ultra high strength steel in some parts of the crucial components. When the high strength steel is about 800 megapascal for the welded joint, welded material is doesn't need the strength need, doesn't meet the strength need for sometimes. And then and it also can occur some problems such as the hydrogen introduced cracking, the softening of the head effect zone, or the decline of toughness. So in order to give some solution for this disadvantage, so we can change some welding processing to improve the welded quality, such as lower the energy of the welding processing, or do the preheating or post-heating treatment, or HFMI. And then another way to change the material just to decrease the welded strength and increase the ductility. And so for this welded joint, maybe it can occur the mismatched welded joint for the high strength then. So my my project is just to study the fatigue property for the mismatched welded joint. So the study aimed to investigate the get the typical welded joints, such as the parted for the shipbuilding structures. There are some typical joints, the parted joints and the non-load carrying welded joints, and the load carrying cruise welded joints. So the aim of the investigating is the fatigue property difference between the base metal and the welded metal, and the low cycle fatigue life of the mismatched welded joint. And then I want to give the fatigue life prediction models for the load carrying cruciform welded joints. And so in the future, maybe this work can be used in the area for the geometry optimization of the RCWG, consider the material property, and then improve the fatigue life of the welded joint. So this is the experiment for the material we have studied. in order to get the property of the steel, so we welded the butted joint, and we cut it the specimen from the plane, and then do the basic mechanical curves. So we can see this is the undermatched welded three-string curves, and the blue and the white is the base metal and the even matched welded joint. So we assume that the base metal and the even matched welded are the same property for the joint, and then this is the this is the property under the cyclic loading. So we can see the same. We can see the property of the strain and the stress curves. This is the monotonic loading, and this is the cyclic loading. So it occurs some the soften phenomenon between this materials, and this is the undermatched welded joint. We can see also it shows some the soften effect of this material, and then we finally we give the ratio, the mismatch ratio between of the materials about 0.7 to 0.8. And the next I have done welded some cruciform welded joint, and using the weld electronic cutting processing to cut the specimen, and then we use this specimen doing the low cycle fatigue test and the high cycle fatigue test. It should be noted that for the high cycle fatigue test, I just used the force controlled condition, and for the low cycle fatigue, we using the extensor to control the displacement, and then there's belongs to different load condition, and for the fatigue test parameter, we use the stress and the strain ratio is about 0.1, and the fatigue frequencies for the low cycle fatigue is so low, 0.5 to 2 HD, and for the high cycle fatigue is 5 to 15 HD, and also the final failure creation is about 30% load drop for the low cycle fatigue, and the high cycle fatigue is completely breakage. This is the result of the failure location. We designed the geometry using the electronic the very electronic cutting processing between the welded tool locations. So we increased the penetration. We increased the crack between the different geometry of the welded root, and then we get the different result of the failure cases. So we can see for the undermatched cruciform joint, and we can see even it has the low, even it has the low the short crack in the welded joint. It occurs the crack from the welded tool, and then when the crack increased, it's a failure from the welded rod. Finally, we see the uneven matched welded joint. We can see with the penetration decreasing and the failure location from the welded root to welded root, welded toe to welded root. So we can see more details about the welded joint. For the welded toe, we can see it from the fusion zone, and for the welded toe root failure is also from the welded zone. And then we summary the fatigue data. We can see it for the welded toe failure. We could not differentiate between this data for the undermatched or even matched welded joint. And then if we can see this data is about the welded root failure. It is lower than the welded root failure life. So we're using the IW standard to compare to this data. We can find the FAT 63 is suitable for the high cycle fatigue of the welded toe failure case. And then FAT 36 is suitable for the welded root failure. Then the material mismatch effect on the high cycle fatigue can be neglected. So the fatigue life are greatly affected by the failure location. So this result is from it's about the low cycle fatigue data, and we fit using the linear relationship, and about the welded toe failure and the welded root failure, and finally we compared the results between the welded failure and the welded root failure. We find that the welded root failure is lower than the welded toe failure. But we can see this picture for the welded root failure. The mismatched hams show some effect for between the undermatched welded joint and the even matched welded joint. So we can find the mismatch effect on the low cycle fatigue of RCW joint should be considered for welded root failure, and the RCW on the welded toe failure have a longer life than the welded root failure. So we put it together in the same diagram, and we can also find this for the low cycle fatigue. We could not find some standard in the IW standard. So we try to using the FAT 160 and the slope 45 for this joint failure. I think it's very suitable for the failure situation. And then in addition, additionally, I used the effective notch strain method to evaluate this data in the diagram, and this analytical solution is from the Japan researcher, and he gives some solution for the welded root prediction, and he also used this analytical solution to predict the welded toe failure as the engineering estimation. But for the low cycle, for this joint, load carrying cruciform joint, we could not to find a solution to estimate the value between the welded root and between the welded toe. So the next step, I want to use the messing confidence curve between the base metal and undermatched metal to predict the welded to and welded rule characterize parameter. And we also used the checkable model to simulate the welded to or welded rule parameter under the elastic and plastic range. And then we're using the energy method to analyze the characterized parameter of welded to and welded rule and compare the different models, and finally we get the transition zone between the welded rule and the welded tool. And finally, we will compare it with the elastic transition range. So this is my conclusion. I should note that the material mismatched effect on the high cycle fatigue of the load carrying cruciform can be neglected. And for the fatigue design purpose, it can be modeled as a homogeneous model. And for the low cycle fatigue, the mismatch effect is not so. It has some effect on the fatigue life, but I think geometry is the most important reason for the fatigue life prediction. So okay, thank you.